All right. So we're sort of done with the basic science of the class, and now we're going to get into some applications, a little more detail about power cycles. So the next thing we're going to talk about is called the Rankine power cycle. And, we're going to be analyzing this using the things that we've talked about. So there's a couple reasons that this is useful to think about. So let's say it has two useful attributes. One, you can do it as a internally reversible cycle. So mostly we'll study it in sort of an internally reversible version. So we'll be able to do some calculations about the ideal efficiencies and stuff that we talked about briefly before, but we'll be able to see where those calculations come from. So we can do some of the calculations that we just used before. But then besides being this way to calculate things for ideal cycles, it also is sort of approximated in actual power plants. So this version of an internally reversible power cycle is actually used. There are infinitely many internally reversible power cycles you could create mathematically, but there aren't very many that they actually implement in power plants and whatever. It's used in coal power plants, oil, just solar, nuclear, biomass, power plants use a version of this cycle that obviously isn't completely internally reversible, but uses this approach. And so what does it mean that all these different types of power plants use this cycle? Well, we're going to be talking about the working fluid, which is going to be water, and that's what's flowing through the pipes. And the stuff listed here is what you use to heat up the water in the boiler of the power plant. So, I think when I first heard about steam power plants or whatever, I sort of was like, oh yeah, but that's from like the Industrial Revolution or whatever. But no, actually water is a really useful working fluid, and steam power plants are still used in all these ways. The thing that's changed is instead of it just being someone shoveling coal into a fire or whatever, you can use all these different ways to heat up the steam. Okay.
That's what nuclear is, right?
Yes, exactly. Yeah, that's listed here. I mean, all these are just the ways that you heat up the steam. Okay, so here's what the Rankine cycle looks like. So I'm going to name these 4 states, and the states are the think of it as like the pipes or whatever between the devices. So there's 4 devices that, and each one of them connects 2 different states. The first device that takes you from state 1 to state 2 is a turbine. And I'm going to draw it like this. And the turbine this is the step that produces the work. So I'll call it W sub T, the work done by the turbine. And so the steam goes from state 1 into the turbine and comes out at state 2. At that point, it goes into the condenser. And at the condenser, you have, let's see, QC, heat leaving the working fluid. Coming out of the condenser, we get to state 3. Okay, so far everything here, if you started with a high pressure at state 1, everything would happen on its own. The high pressure goes into the turbine lowers the pressure, so that's gonna drive this motion from 1 to 2 by itself. The condenser is cold, that lowers the pressure more, and so the the working fluid is gonna just keep on moving on its own. But at some point, we have to get from a low pressure coming out of the condenser back to a high pressure to power the turbine. So that happens from step 3 to step 4, and that's just done with a pump. And for the pump, you need work to be done on the fluid. So the work done on the fluid is W sub P. It comes out of the pump at state 4. And then the last step in this cycle is the boiler. And at the boiler, heat is added to the fluid. So this is QH. So this is the ideal Rankine cycle. We'll see that in practice they modify some of this a little bit. And here is the stuff that we're going to use about these different steps. Anybody have any questions about? Yeah.
I do.
Yeah.
So why do we put it into water? Why isn't there a way to just take the heat directly from the coal and turn that into the work?
Mechanical energy.
Well, something has to, the work that you get out of it is done by something expanding, you know. And then I guess in this case, it's done by, so you have.
I mean, you could turn a turbine with air.
So yeah.
Effective.
Oh, so to go from, so why do we have water instead of air? Because you get a huge difference in pressure by going from liquid water to steam, you know, a huge difference in specific volume. you know. And you can do that with air too, but you'd obviously have to get a really low temperature in order to turn the air into liquid, you know. So basically, in the working fluids of all these different cycles,
Is there a loss going into phase transitions like that?
is there what?
Is there a loss by going into phase transitions? Like,
No, not necessarily. I mean, there are losses, but there's nothing requiring an energy loss or anything. But yeah, like in all these cycles, refrigeration, heat pumps, and power cycles, they're always using a working fluid that's operating right at that phase change state, you know, because they're trying to take advantage of, I mean, like, I think the simplest way to think of it is what they're trying to take advantage of is latent heat, you know. When you remember that when you, if you have constant pressure and you start with a saturated liquid, okay, and then you boil it to get a saturated vapor, you get this huge increase in internal energy without any corresponding temperature increase. A temperature increase would make it harder to keep pouring energy into this or pulling energy out of it. But since that temperature is constant, you get all this energy added to the fluid without the difficulty of the temperature rising or falling at the same time. And that's why all working fluids are used right around, I shouldn't say all, but all the ones I've read about or whatever are operating right at that point where they can be at a liquid at one point and then at a vapor at another point.
It's ideal. It's going to take a lot of energy to get it up to that point.
Yeah. I mean, all of this stuff you could do without a phase change, but you just get a lot more energy transfer if you're at the phase change.
Gotcha. And is that what the pump is for? Because I would think that the boiler alone, doesn't that pressurize it in and of itself?
Well, you have to get it to the boiler, you know?
Got it.
Yeah. Like somewhere you have to go from a low pressure to a high pressure, and that's where you have to put the pump.
Got it.
Yeah.
It just cycles it.
Yeah.
The only thing that doesn't use that principle is an air cycle machine. And it works on high volume.
Huh.
So.
Yeah, that's interesting.
Actually, it doesn't use a phase change. So
Uh-huh. Yeah. Any other questions? Okay. So let's talk about these steps. I mean, I think, so first of all, just remember to just take the time to make sense out of the different steps, what it's doing. It's pretty intuitive if you think about it for a second. So here are the steps of the ideal Rankine cycle. From state 1 to 2 is an isentropic, that's important, expansion through the turbine. It's expanding because it's high pressure as it goes into the turbine and low pressure as it comes out of the turbine. And this is where we generate the power. W sub T. And so what this says, isentropic, means that the entropy doesn't change as it goes through the turbine. So we have this important relationship that the specific entropy at state 1 is the same as the specific entropy at state 2. Okay, we're going to use that all the time. From state 2 to state 3, it's not isentropic. Well, state 2 to state 3 is the condenser. There's obviously heat transfer, so it can't be isentropic. An isentropic process has to be no heat transfer and no irreversibilities. It has to be internally reversible. So, but this happens at a constant pressure, so constant pressure heat rejection at the condenser. And so what we know here, since it's constant pressure, is that the pressure at state 2 is equal to the pressure at state 3. Then from 3 to 4, we're going through the pump. This is another one where there's no heat transfer. And this is an ideal cycle that we're thinking about right now. So again, this is isentropic. So this is isentropic process. To pump the liquid to a higher pressure. Since it's isentropic, we know that S3 is equal to S4. And then from state 4 to state 1, this can't be isentropic again. It's a constant pressure addition of heat at the boiler. So P4 has to be equal to P1.
You put process instead of pressure on that.
What?
You wrote process instead of pressure on accident.
Constant, yeah. Okay, so we're going to think about this in terms of a temperature-specific entropy diagram. So temperature is on the vertical axis, specific entropy is on the horizontal axis. You can see the vapor dome. And so because the vapor dome's there, you can look at this diagram and always tell what the state of the working fluid is at every point. So state 1 is up there. Let's see, I'll write the states below, but what's this? So state 1 is, as it comes out of the boiler, going into the turbine. What does it say the state is at that point, the phase?
It's gas.
Yeah, and it's saturated there. If it was superheated vapor, it would be out here. And we will have modifications that do that later. But in the ideal cycle, it's a saturated vapor. Then state 2 is down here. So now it's come through the turbine. Notice that you can see that the entropy is constant over that process. So this is the turbine. Then from state 2 to state 3, we're over here. This is the condenser. And so coming out of the condenser, what's the phase of the working fluid? Saturated liquid, yep. And then it goes to the pump. And so after the pump, it's a compressed liquid. And then to get back to the turbine, it goes through the boiler. And that happens, so first you have to heat it back up to the state one, first you have to get it up to the saturated liquid. And then you have to add heat to go from a saturated liquid to a saturated vapor. So that step from 4 to 1 has sort of 2 legs in the journey, because you have to get up to a saturated liquid and then change the phase. So all of this is the boiler. And this is a TS diagram.
So the heat actually increase, the temperature actually increases.
Yeah.
Inside the pump.
So the pump, the pump changes the pressure, which it does. I don't have much to say about that. Any other questions right now before I? Okay. All right, so before I get into starting to talk about some calculations and stuff, this is what we'll do eventually. So later we'll consider 2 improvements to the efficiency in practice. The first one is superheat. So we'll see that you can get more efficiency if instead of just the boiler taking the working fluid to a saturated vapor, you get to the saturated vapor and then heat it up more into a superheated vapor. So that looks like this on the TS diagram. So you get to the saturated vapor, then heat it up a little more. Everything else stays the same. And the second improvement is reheat. So for a reheat, you have the saturated vapor, you superheat it, then you have 1 turbine, you heat it again, send it through a second turbine. And the other stuff looks the same. And that's because we're going to see that you get better efficiency if you have a higher temperature and a higher pressure coming out of the boiler, going into the turbine. So this is going to be 2 turbines. And with the 2 turbines, we're also going to do this where we get into a liquid vapor mix coming out of the second turbine. Okay, so the first time we talked about cycles was it was in the section where we were talking about the Kelvin-Planck statement of the second law, and I kind of just gave you all these measures of efficiency. Some of them you could sort of make sense out of, like it makes sense that the efficiency of a power cycle would be the work that it produces divided by the heat that you have to put into it. But then some of it, I just kind of threw, like an ideal power cycle, I said, was 1 minus temperature at the condenser divided by temperature at the boiler, and I just sort of stated that. But now that we have a power cycle that we're very specific about, we can actually calculate some of that stuff. So I want to go through, so the next thing I want to do is show that the ideal efficiency of the ideal Rankine power cycle. That's sort of redundant, but is 1 minus the temperature at the cold reservoir divided by the temperature at the hot reservoir. And we're going to use the specific stuff that we know about this cycle. Okay, so since this is internally reversible, we know that a change in the entropy is equal to the heat transfer divided by the temperature. Okay? That's the definition of a change in entropy. And so we can write this as m d little s and then TDS, do the algebra here, and you get TDS is equal to dq over m. Now you can integrate both sides of these, and you get, so q over m, which we know can also be written as q dot over m dot, is equal to the integral of TDS, m dot. And so q dot over m dot is equal to the average temperature times the change in the specific entropy. Okay, so we have this result. And now we're going to think about the different, processes. So from process 1 to 2, that's the turbine. There's no heat transfer there, and it's isentropic. So these are both equal to 0. And now the condenser. Q dot over M dot is equal to the average temperature of the fluid at the condenser times the change in specific entropy. This expression assumed that Q is heat added to the system. At the condenser, Q dot C is heat leaving the working fluid. So we have negative QC dot over M dot is equal to the average temperature times the change in entropy. And we can write this as the average temperature of the working fluid in the condenser times what's the change in entropy. That is, so this is our state. We're going from state 2 to state 3. So the change in entropy is specific entropy at state 3 minus specific entropy at state 2.
Temperature change is generally linear, so it's just tie temperature by flow temperature over 2.
I don't think there's any reason to assume that. You'd have to do the integral average, Okay, state, what are we at? State 3. So state 3 to state 4. This is the pump. This is isentropic. So Q dot over M dot. How did I write that before? Which is equal to T average, TDS is equal to 0. That should be a delta. And then finally, 4 to 1, this is going through the boiler. So Q dot over M dot is equal to the average temperature times the change in specific entropy. This time, positive QH is going into the working fluid. So this is QH dot over m dot is equal to T average times the quantity specific entropy at 1 minus specific entropy at state 4. Okay, so now we're going to use the fact that, like, think about the isentropic processes. There's one at the turbine, and that says that S2 is equal to S1. And there is one at the pump, and that says S4 is equal to S3. And so if our efficiency is 1 over QC over QH, we can write that as 1 minus QC dot over M dot divided by QH dot over M dot. And that's equal to 1 minus. So now we're going to make the substitutions in those two, the two expressions that we had for the boiler and the condenser. So QC over M dot is, notice you have to switch the order of these two specific entropies. So we have TC average times the quantity S2 minus S3 because of that negative. And now we're dividing that by QH dot over M dot. That's at the boiler. And that's temperature, so I'll write this as the average temperature at the boiler times S1 minus S4. Because of the isentropic processes, we know that we can replace 2 with 1 and 3 with 4. And so you get TC average times S1 minus S4 over TH average times S1 minus S4. These cancel. And you get an ideal efficiency of 1 minus the average temperature at the condenser divided by the average temperature at the boiler. Whew. Yeah. So when we talked about like efficiencies and performance and stuff before, we couldn't verify that this equation was true because we didn't have a specific cycle in mind. But now that we have this specific thing in mind, we can, go through calculations like that. This is what we had before. And this step here is because S1 is equal to S2 and S3 is equal to S4. Okay, so we're going to often, like, when we're doing these analyses, we're going to take advantage of those isentropic steps to be able to replace the specific entropies from one to the other one. Okay, what time is it? Okay, so now what we're going to do is we're going to represent the efficiencies of these cycles in terms of entropies, enthalpies at the different states. And then I'm going to just give some examples of, since enthalpies are properties you can look up in a table, what we're going to see for problems is you have this cycle and you know the pressure and temperature here, you know the temperature here, the pressure here. How can you go around using what we know about this ideal Rankine cycle and figure out what the efficiency of this thing is? Okay, so and we're going to use that to calculate the efficiency given different temperatures and pressures. Okay. So the first thing we're going to do is talk about the step that goes from 1 to 2. This is the isentropic expansion through the turbine. All of these processes, we're going to do control volume approach. So we're always going to start with the control volume first law. So start with the control volume first law. So we have dE dt for the control volume is equal to Q dot minus W dot plus MI dot times the quantity HI plus VI squared over 2 plus GZI minus ME dot times the quantity HE plus VE squared over 2 plus GZE. We're going to assume it's steady state. We're going to assume there's no heat transfer. And we're going to assume there's no change in speed. I guess I usually write that as kinetic energy or potential energy. There obviously is a change in speed, but it's not significant compared to the change in pressure. So that goes away. There's no heat transfer. The m dots are the same. Those four things cancel. And you get that W dot for the control volume over m dot. So this is like a rate of work being done by the turbine is equal to H. Well, the H at the inlet is H1. At the exit, it's H2. And so that's an expression for W dot over m dot for the turbine. Second, from 2 to 3, this is the constant pressure heat rejection at the condenser. Again, we're going to assume it's steady state. We're going to assume potential energy and kinetic energy are roughly constant. And this time, there is obviously heat transfer, but we're going to assume it's no work done. It's just a rigid device. So work dot is equal to 0. So dE dt is equal to Q dot minus W dot plus M dot times the quantity HI plus VI squared over 2 plus GZI minus M dot times HE plus VE squared over 2 plus GZE. We're ignoring the work, potential and kinetic energy, and dE dt. So this time you get that, so we have Q dot for the control volume is equal to M dot times, this time it's H exit minus H inlet. And so Q dot for the control volume divided by M dot is equal to H at the exit, which is 3, minus H at the inlet, which is 2. What we're calling positive Q dot at the condenser is heat leaving the system. And so we'll write this as Q dot for the condenser over M dot is the negative of this, so is equal to H2 minus H1. And this step is because QC dot positive is leaving the system.
Is that considered I guess, waste or.
Yes, that's right.
We're losing that, and
That's right.
the
That's
greater that is, the less efficiency we have.
the greater, yeah, that's right. If nothing else changes,
And
yes.
That's why you have a double turbine in order to get the temperature down lower.
I think the biggest reason is to get the pressure and temperature up in the boiler, or get it up going into the turbine. But yes, you are right that you want to get that low. We'll talk about some other like practical considerations later on. Like one thing is you don't want the temperature and pressure too low coming out of the turbine, because then you get a phase change. And even though mathematically that's not bad for the turbine, having liquid in your turbine is really hard on the equipment, you know? So, okay, so we'll just continue with this next time. And then we'll get into some problems.
Did you say that H1 is equal to H3, or is that supposed to be H2 minus H3 instead of?
Oh, I'm sorry. H2 minus H3, thank you. Yes. Yeah, be sure you make that change in your notes. But at the end of all this, we're going to have this big expression for the, a big expression for the efficiency of this system in terms of all these H's. And then we're going to make substitutions of the H's that are equal to each other and come up with a nice concise form in terms of just, I don't remember how many, 2, something like that. Okay, that's all.